This is a tutorial to explain how to find the error of approximation between a Taylor series and the trapezium rule. Firstly, we have an f of x function up here, which is going to be the function we're working with throughout this video. And what we want to do is to firstly approximate this integral between a range of a value of x, which we're going to call xk, and x for this function f of x. The first thing we're going to do is we're going to define a function g of x, which is equal to the integral of f of x. And therefore, we know that the derivative of g of x is going to be f of x, and the second order derivative of g of x is going to be the first order derivative of f of x, and that will continue on and on. We need to use that later. Another thing we're going to define here is that the difference between a value of x and its previous value we're going to call h. So this is going to be a consistent difference between values of x, which is going to be our interval. Therefore, we can say that the value of xk plus 1 is equal to xk plus this width h. So the first thing we're going to do is that we're going to say that the integral between a value of xk and a value of xk plus 1 of f of x is equal to g of xk plus 1. So we don't know what g xk plus 1 is, so we're going to use a Taylor approximation of the third order of g of xk plus 1 to find out what that could be. So we do a normal Taylor expansion, gxk plus 1, and that approximately gives us gx of k over 0 factorial, so that's 1, and the first order derivative of gx of k times the width h over 1 factorial, so 1 again, and then the second order derivative times h squared over 2 factorial, and the third order derivative of xk times h cubed over 3 factorial. So when we want to try and work out what these functions are, we don't know what g of x equals, we only know what f of x equals. So we want to convert these back into fx values using these rules that we defined up here. So for gx of k, our first value here, if we plug in this value into the top of our integral up here, which is this one up here, then we're integrating the function f of x, because g of x equals this integral here, between x of k, but also x of k. So there's no difference between these intervals, so there's going to be no area under this curve because we're taking the same point. So this equals 0, which is nice. Our first order derivative of g we know equals f of x. Our function of f of x is up here, so as we're taking this at the point k, this is whatever this value of x is at point k cubed minus xk plus 1. Our second order derivative, we're just going to, this changes into the first order derivative of x, so we're just going to take the first order derivative of this function, which gives us 3xk squared minus 1. And the same thing here with the third order derivative equals the second order derivative of f of xk, which equals 6xk. So then we're going to take these values that we've worked out here, and we're going to put them back into our approximation here. So we have gx of k plus 1 is approximately 0, our value here. F of xk half, this comes from our 2 factorial here of the first order derivative of f of xk, and times that by h squared, plus 1 over 6, 3 factorial, times the second order derivative of f of xk times h cubed, and this was, as we saw, g of xk plus 1 is approximately equal to, is equal to the integral here as defined up here. So then if we plug in these values for f of xk using here, we now know that that gx of k plus 1, which is equal to this integral here, is approximately equal to 0 plus our f of x, so xk cubed minus xk plus 1 times h, plus half times 3xk squared minus 1 times h squared, plus 1 over 6 times 6xk h cubed. So that's our Taylor approximation. So then we're going to move on to the trapezium rule. So the trapezium rule is fairly simple. You take the length of the first side add the length of the second side, b, times that by what is normally the height, but as we've flipped on the side, it's the width of the interval, and then we're going to half that. So then, simply, the length of a, this side here, is just going to be from 0 to f of xk, so that's just f of xk, and the same for b, we're going from 0 to f of xk plus 1, so the length of that side is f of xk plus 1, and we've already defined earlier that xk plus 1 minus xk equals h. So when we plug that into our trapezium rule formula here, we then get half times f of xk plus 1 times h. So then, because we don't know what this function is here, we only know what f of xk is from earlier, which was this function here, we then need to do an approximation for what this function is going to be. Now, that means we just get to use Taylor again. But this time we only need a second order, because later on we're going to be multiplying by h again, and we want two terms that are in h cubed so that we can nicely subtract them from each other. So f of xk plus 1 is approximately going to be equal to f of xk over 0 factorial. It's the same expansion as earlier, so the first order derivative times h over 1, and the second order derivative times h squared over 2. Then we can plug in our function from earlier, so our f of x function. So we know that f of xk plus 1 is approximately equal to our f of x function, our first order derivative times h, and half, which is our 2 factorial here, times our second order derivative times h squared. So then, with our trapezium approximation of this integral, we know that the integral can be approximated by the trapezium rule. So the integral we were looking at earlier between xk and xk plus 1 of f of x is approximately equal to half times f of xk plus f of xk plus 1 times h. So we're then going to plug in our approximation of f of xk plus 1 into this formula and expand it out. So then we have half times f of xk plus f of xk, because that's our first term from up here, plus the first order derivative, this term up here, times h, and plus half times the second order derivative times h squared divided by 2. And then from our formula up here, this h just sits on the end here. So then what we're going to do is just plug in our f of x function again. So we then have half times f of x again, the first order derivative times h, and half times the second order derivative times h squared, and all of that we're going to times by h again. So if we then expand that out one final time, we get to this term here. So we have our f of x function times h, half times our first order derivative times h squared, and a quarter times our second order derivative times h cubed. So then finally we just need to find the difference between these two, and this is what we're going to call our error. So we recall from earlier our Taylor approximation was this term here, so our f of x times h plus half of the first order derivative times h squared plus a sixth times the second order derivative times h cubed. Trapezium approximation gives us a very similar result. So the first terms are the same, those two are going to cancel. The second terms are the same, those two are going to cancel. And there's a very small difference between these last two, which is minus 1/12 of the second order derivative times h cubed. So when we plug our function in, so that was this function up here, what we end up with as a result is 1 over 6 times 6xk times h cubed, and we go to minus a quarter times 6xk times h cubed, and this gives us a half times xk times h cubed, which we then are going to call big O h cubed, and that is our error.